Today, we're going to deal with our first conservation law, conservation of mass. This is most applicable to open systems. In closed systems, no mass enters or leaves, so the mass is definitely conserved. For open systems, mass can both enter and leave, and the conservation of mass principle is one way we can keep track of these changes. We have briefly touched on the first law of thermodynamics, which states that energy cannot be created or destroyed. We will actually look more deeply into this concept in the next video, but for today, we're going to focus on conservation of mass. To keep track of mass coming in or out of a system, we can incorporate the mass flow rate. This is the amount of mass flowing through a certain cross-sectional area per unit time. It is denoted by m dot. We saw this briefly a few weeks ago, but today we're going to go through it in depth. Looking at an incremental area dA, the mass flow rate will depend on the density of the fluid, as well as the component of velocity perpendicular to the area dA. Therefore, the incremental mass flow rate, delta m dot, is equal to rho, the density, times the dot product of the velocity v and the incremental area vector dA. Alternatively, the mass flow rate can be calculated by integrating this expression to get that m dot equals the integral over some area of density times the normal component of velocity passing through that area. A related concept to this is the volume flow rate, which is somewhat confusingly sometimes called flow rate. If there was no word in front of flow rate, it means volume flow rate. This is the volume passing through a certain area per unit time and is denoted by v dot. This is basically the same as the mass flow rate, but without the density. So v dot is equal to the integral over the area of the normal component of velocity. From this, the average velocity can be defined by dividing out that area, as seen in this equation down here. If we use this definition of the average velocity, then the volume flow rate is simply equal to this average velocity times the cross-sectional area. Note that the AV subscript was dropped in this final version. Usually when you see just simply v as velocity, it means the average perpendicular velocity. We can similarly redefine the mass flow rate to be equal to the density times the velocity times the area, or m dot equals rho VA. This is as long as the density does not vary much across the area, which doesn't happen often. The way we actually implement conservation of mass is with something called control volume analysis. The control volume essentially defines what you're going to care about. Then surrounding your control volume is something called a control surface. It is this area that you then need to keep track of anything going in or out. This basically becomes the area in the area integrals we saw on the previous couple of slides. And note that this can actually change in time. Sometimes this makes the analysis easier, sometimes it makes it harder, but it's up to you. In terms of conservation of mass, what we are going to care about today is the amount of mass inside our control volume, as well as the mass flow rates across the controlled surface. As an example, I have a jet engine here. The mass of air inside the jet engine is my control volume. My control surface is basically the exterior of the jet engine. And then to know the amount of mass inside the control volume at any time, I'm going to need to track the mass flow rates into inlet area 1 and out of the exit area 2. The amount of mass contained within the control volume at any time can be found using this equation. The mass of my control volume, mCv, is the integral over the control volume itself of every incremental element of mass dm, which can be converted to density rho times the elemental volume dv. Then we need to track how this changes in time along with the incoming and outgoing masses. To begin the analysis, let's consider a control volume as shown down here on the left. The system we care about is the blue shaded part. Notice that our system actually extends beyond the control volume. So at time t, our system consists of a bunch of mass inside the control volume, as well as some mass that is coming in, delta m in. At some later time, t plus delta t, the mass coming in is all the way inside the control volume. But now some of our system has left the control volume up top, as seen here on the right. This amount of mass heading out is delta m out. At time t, the total mass within our system is msys at t equals mcv at t plus delta m in. That is from the picture on the left in the previous slide. at time t plus delta t, the total mass in our system is msys at t plus delta t equals mcv at t plus delta t plus delta m out from the picture on the right. The rate of change of the mass in our system is then, from the definition of a derivative, dmsys dt equals the limit as delta t goes to 0 of msys t plus delta t minus msys at t over delta t, which is equal to the rate of change of mass within the control volume, dmcv dt, plus the mass flow rate going out, m dot out, minus the mass coming in, m dot in. Notice the signs here because they may seem a bit weird. It was not explicitly stated earlier, but the area vector dA always points outward from the surface. So velocity flowing outward becomes a positive mass flow rate. V and dA are in the same direction as vectors, whereas velocity going in gives negative mass flow rate. The dot product gives you a -1. This is in agreement with what we see here in this equation, which is good, even if it does seem a bit weird right now. Using the principle of conservation of mass, we know that the mass in the system cannot change. Therefore, dmsys dt has to be 0, which means that the change in mass of the control volume, dmcv dt, is equal to the mass flow rates coming in minus that going out. Notice that the signs probably make a bit more sense now. This is basically just saying that the change in mass inside the control volume is whatever comes in minus whatever comes out, which you probably already knew, but it is good to have it confirmed. There are actually many ways in practice that we can apply the law of conservation of mass. We just saw one dealing with mass flow rates. We can also do it using densities and velocities. The most general way to do it is to leave it in integral form and have d by dt of the integral over the control volume of rho dv plus the integral over the control surface of rho v dotted with dA is equal to 0. This first term is how the mass is changing inside the control volume, while the second term takes into account the mass coming in and out. Using the average velocity, this integral over the control surface becomes a sum of mass flow rates coming in and out, as seen down here. And there are many other options as well. Many of those options begin with simplifications to the system. If we have steady flow, then nothing changes in time. So the first term, the change in mass inside the control volume, is 0. This then reduces to the mass flow rates in and out must be equal. Or using the average velocity, we have rho VA equals a constant, or rho 1 V1A1 equals rho 2 V2A2 at any points 1 and 2. If the fluid is incompressible, then the density is constant, or rho 1 equals rho 2. So this reduces to V1A1 equals V2A2, or V dot in equals V dot out. The form that is used basically depends on which one of these regimes we are in. So here is your pre-lecture example for today, along with the answer. We can go over the solution as well as any questions you may have later in class.